So welcome to Math 355, Section 2. This is Lecture 3. And so what we're going to do today is we're going to do an introduction to groups. We'll be talking about some examples. We'll be talking a little bit about some proof techniques. And we will try to link this to some of the stuff we've already seen. I mentioned in Section 1 that I have deliberately not looked at some of the proofs to try to give myself an opportunity to show you how a mathematician thinks about things. The problem, of course, of teaching two sections back to back is I've now looked at things from the first section. So it's going to be hard for me to say, gee, I wonder what we should do next after having just done this an hour earlier. This is also one of the reasons why I want us to consider somewhat flipping the class. So half the time you get the lecture live, half the time you watch the lecture, and in this way we can just do more problems. So today we'll come to a lemma where we'll only do two statements, and I'll leave the other two for you to think about. Okay. So the first is you're trying to come up with examples of groups. And so a really good source is permutations. So can someone define what is a permutation? We have, S. Excuse me. So S is a set with n elements. Maybe we label them x1, x2, ... xn. What would be a permutation of this set? You flip the order, good. And how many permutations are there? Have n factorial permutations. That's a lot of permutations. And so we want to come up with what's a good way to represent all the different permutations or to represent a specific one notation is I can write 1, 2, ... n minus 1, n, and maybe a1, a2, ... an minus 1, an. And this means 1 is sent to a1, 2 is sent to a2, and so on. So this is pretty nice notation. I can quickly look down and see. Now, if you have a set with 10,000 elements, however, you're not going to want to write something like this. And so you're going to often have to come up with formal ways of doing things. Every now and then, we will justify the fact that this course has prerequisites. So one of the prerequisites for this course is linear algebra. So hopefully you've seen permutation matrices before. But if not, let's write this down in matrix form. So let's say we know that I goes to J. So here's my permutation matrix. Here is EI. So it's a 1 in the ith spot and 0 everywhere else. And here is EJ, 1 and then 0 everywhere else. So we want to send I to J. And I claim this gives us information about the matrix. So do you know anything about any row or any column of this matrix? What do you think? So we have to take the vector that's 1 in the ith spot and get back out 1 in the jth spot. So does this give you information about any of the rows or any of the columns? Well, if you think the way you do matrix multiplication is you take the row here with the column here, you take the dot product, and that gets you the element here. So it's going to give us information about one of the rows of A. Which row is it going to give us information about? Well, if I give you information about EI, right now I'm just telling you I goes to J.
So it's not actually like 3 rows, you just wrote it.
I just wrote like that. Everything else is 0. If you want, I'll write more. So here it's 0, ... 0, 0, ... 0. Here's a 1, 0, ... 0, 0, ... 0. I have a 1 in the ith spot. I have a 1 in the jth spot. So which row do we know for the matrix? We know the jth entry here is a 1. We know something about the jth row here. The jth row has to be a 1 in the ith spot, 1 in the ith spot, and 0 elsewhere. And that's because I goes to j. We can also use this probably to get information about a column. We know I doesn't go to anything else. So we could actually probably extend this. What must be true about the ith column of this matrix? It should be zeros everywhere else. Yes?
Why should be zeros? I mean, if you multiply
Oh.
with zeros.
Oh, sorry. Wait. You're right. We're multiplying with zeros. You're right. Sorry. You're right. We know there has to be a 1 there. You're right. And then we know it has to be 0 everywhere else going up like this. Yes. Sorry. Thank you. So it should be the ith column. Thank you. So the ith column, we have to have a 1 in the jth spot, and a 0 everywhere else. And then we can keep doing this for each one of these. So we can start to deduce some structure about these matrices. So what can you tell me about the structure of permutation matrices? What do you think must be true about the rows? So each column has to have one spot that's a 1 and everything else is a 0. Could we have one row that has multiple 1s in it? Or would that cause problems? If you think about it, if you have a row that has multiple 1s, you're going to have 2 different elements sent to the same thing. Each row has only 1. And imagine the matrix starts off with 1, 1 in the very first row. Then the vector E1 would be sent to 1, and the vector E2 would be sent to 1. You can't have 2 different things being sent to the same thing. It's a permutation. I have n objects that have to be reshuffled. I can't have 2 things sent to the same. So I have a matrix of 0s and 1s. Each row has a 1 and the rest 0s. Each column has a 1 and the rest are 0s. What do you think the product of 2 permutation matrices is? It's another permutation. So this is not obvious. If you take 2 matrices that are just 0s and 1s and you multiply them, it's not immediately clear that you're going to get a matrix of just 0s and 1s of the same form. So permutation followed by permutation is a permutation. This is very similar to what we saw with the Caesar cipher. If I take a Caesar cipher, if I shift by 3 and then I shift by 5, that's the same as shifting by 8. So now they all be distinct. What would it mean for them all to be distinct? Well, again, what can you tell me about the structure of the matrix? How many matrices are there? N factorial. Right, so only n factorial matrices permutation, and there's only n factorial possible permutations. Each one has a matrix. So since all of these are permutations, there's only n factorial possibilities. But another way of looking at it is, look, each matrix, every element is either a 0 or a 1. Forget the restriction that you can only have one row, one in each column, and only one in each row. There's there's two choices for every entry. There's n squared entries, so there's 2 to the n squared matrices. So you have to repeat. So say p to the a equals p to the b, and without loss of generality, we can assume a is greater than b. So a equals a minus b plus b. And so without loss of generality, one of them has to be greater. This is the pigeonhole principle. So if we look at p squared, p to the n factorial plus 1, at least 2 the same. Because we have too many pigeons, so one box has to get at least 2 things. So this means, so p to the a equals p to the b, that means p to the a minus b, p to the b equals p to the b. And I want to claim this means p to the a minus b is the identity. But no matter what permutation you take, eventually you have to get to the identity. So again, you've all seen multiplication. When I basically want to take the inverse. So if I have a permutation matrix, is there an inverse to a permutation matrix? Yeah, instead of sending I to j, what do? What would be the inverse of sending I to j? J to I. And so given any matrix, we can always undo it. And so we can invert. And so, you can prove this rigorously, but we know how to find the inverse. So we can keep applying the inverse of p b times, and then we'll get p to the a minus b is the identity matrix. So no matter what permutation matrix you start with, if you apply it enough times, you end up getting nothing. You get the identity, you just return to where you started. So this is a nice result, and we'll see similar examples of this later. Okay, so now it's time to formally define a group. This is one of the most important objects that we will be studying. I prefer a slightly different definition than is in the book. The way it's defined is something that's implicit. And so there's really another property. G is closed under the binary operation. So that means G1, G2 in G implies G1 dot G2 is in G. So this property is called closure. And when you look at this, that's implicit in the definition. It says a group consists of a set G and a composition law that takes G cross G to G. Well, as soon as you say it takes G cross G to G, you're forcing it to be closed. Not everything is closed. Sometimes when you, for instance, if I do integers under division, the integers are not closed under division. Can I divide 5 by 2? Yes. I'm not going to get an integer. So I leave the space of integers and I have to look at maybe a larger space, but I can definitely do the operation. And so here we want the set to be closed under the composition law. And we typically use a dot to represent the composition. If the order doesn't matter, if G1 dot G2 is the same as G2 dot G1, we often use a plus sign to just emphasize that the order doesn't matter. This can be a little confusing. You could have several groups being studied at the same time, and the dot can mean different things for different groups. Usually it's clear from context. If it's not clear, you can put on a little subscript to say, this is the group multiplication from big G. And now we get to the key identities. The key axioms. So the first is the identity axiom. There is some element E such that no matter what G you take, E times G is G times E is G. So there's some element that does nothing. Most of the time, it's clear what the identity element is. If you're doing matrix multiplication, what do you think the identity element would be for matrix multiplication? The identity. And if you did matrix addition, what would the identity element be? The zero matrix. So again, most of the time we know what it should be. But it's telling you that in order to be a group, there has to be an identity element. The next is the inverse. You give me anything in G, then there is some element H such that G times H is H times G is E. So every element can be inverted. So sometimes you could write H as maybe H sub G. And I can put the little sub G to tell me that this element H depends on G. In the previous one, when we talked about the identity, it's not you give me a G and there's some E which depends on G such that I can multiply and it's not going to do anything. No, it's no matter what G you take, there's an element E that works for all of them. Well, not surprisingly, when I'm finding the inverse of an element, the inverse depends on the element. And I could write it as H sub G to remind myself that H depends on G, but there's better notation. And the notation is, we're used to using -1 to denote an inverse, so why don't we denote the inverse of G by G to the -1? And if you think about it, if you just do the standard power notation, G to the -1 times G is G to the 0, anything to the 0 should be 1, and 1 is the generalization of the identity. This is just good notation so that you can quickly look down, and when you see G inverse, that's just telling you this is the inverse of G. Okay, the next is the associative law, that I can only combine things 2 at a time. So if I give you G1.G2.G3, it's not clear. Am I first combining G1 and G2 and then taking that and combining it with G3? Or am I combining G2 and G3 and then combining that with G1? Well, the associative law says it doesn't matter. We're only going to look at spaces where this is true. There are situations where the associative law fails. Fortunately, it holds for matrices, and matrices are a great source of groups. The last one is, we say a group is abelian after the mathematician Abel, or commutative if the order doesn't matter. If G1.G2 is G2.G1. It's not required for that to hold. It's nice when that holds. There are lots of examples of groups that are not commutative here. If you look at matrices, matrices would be a great example. I like to do a lot of stuff with Rubik's Cubes. Rubik's Cubes, very non-commutative. All right, so these are the key quantities. You've actually seen a little bit of associative in the past, but it may not have been made that explicit. So here's the result from calculus. The derivative of a finite sum is the sum of the derivatives. Okay. So this is a great result. And the way you prove this is by induction. And you first do the base case. You show f plus g prime is f prime plus g prime. So hopefully you saw that in your calculus class. And basically you just show the limit of a sum is the sum of the limits, so long as at least one of the limits is finite. Now, For the inductive stuff, I'm only going to do n equals 3, but you should do the general case. So let's say I give you f plus g plus h, and I want to find its derivative. I can group f and g together. And now, what are my two functions? So when I group them like this, what are my two functions? F plus g is one function. What's the other function? And now that I have two functions, I can use the base case. And now this is just the derivative of f plus g plus the derivative of h. And just being extremely pedantic, its derivative of f prime plus g prime is the first one. The second one is the derivative of h. And now I can use the fact that addition is associative. And that would be the proof that the derivative of a sum of three functions is the sum of the three derivatives. You can do this for any finite sum. It does not always hold if you have an infinite sum. This is almost surely new. Most calculus classes do not cover this. They just show, yeah, the derivative of two functions is the sum of the derivatives. So if I give you a polynomial, you can just differentiate term by term. Almost surely they did not actually prove that. This is what you need to do to make this rigorous. And again, now that you're going further in mathematics, you should be aware of stuff like this. Okay, so these are the key properties of a group. Yes?
Are the identity and inverse three?
Great question. And if we go forward one slide, so exactly what you would wonder. And these are the types of questions you should be asking. Is there a unique identity that works for everything? And it turns out, yes. So each group has a unique identity element. Each element has exactly one inverse. The inverse of GH is H inverse G inverse. And if G is in G, the inverse of the inverse is the element. So which of these statements do you think is the easiest to prove, A, B, C, or D? Oh, Professor Miller, you're so great. You've been doing this for so long. We know you can do all of them without any trouble. One of them I think is actually easier than others. Or at least two of them I would focus on. Any thoughts? The last one or the second to last one? Because they're telling you what the inverse is. We're claiming that the inverse of GH is H inverse G inverse. Let's just check that by brute force. So if they said your GH is invertible, and there's a nice formula for its inverse, then that would be a little bit harder because I'm not telling you what to prove. But here you're being told what to prove. So let's prove let's prove C. So proof of C. So let's look at H inverse G inverse times GH and GH times H inverse G inverse. So I first have to group things carefully. I have to group things into pairs and always combine them. So the first one, I have H inverse GH. The second I have GH, H inverse G inverse. Which items do you want to pair together in the first? Yeah, G inverse and G. And in the second, you would pair H and H inverse. And then I'll pair it with H in the first one and then G inverse in the second one. And again, I am being extremely pedantic and just going through all the steps in terms of how we do things. Because it's associative, I don't really need to worry about this. I can just leave it like H inverse G inverse GH, G inverse times G is the identity, and the identity times anything is the itself. I'm going to just put in all the details because it's early in the semester. I hope this does not turn you off from mathematics. So it becomes H inverse times EH, and the other is G times EG inverse. Well, what's the identity times H? So the identity times H is just it's just H. And the other one, it's going to be G inverse. And then by definition, these are just the identity. And the filled in square is the QED symbol, means we've reached the end of the proof. So that's how you would prove C. This is similar to things you might have seen in linear algebra. If I give you the inverse of a product of matrices, it's the product of the inverses in reverse order. If I give you the transpose of a product, it's the product of the transposes in reverse order. And you can see why the order is reversed as we pushed everything out here. So this proves C. D is similar. So it's a good exercise. You should prove D. Okay. So now we can do either A or B. Let's do A. Proof of A. So I could either try to do some kind of constructive argument and show that there's only one element that could possibly satisfy it, or let's assume that there are two elements that are identities and show that they must be the same. So let's assume E1 and E2 are identity elements. So for all G in G, we know E1G equals GE1 equals G, E2G equals GE2 equals G. That's what it means to be an identity. No matter what element you take, when I multiply by the identity, I get back with what you started. So this is true for any choice of G, and the second one is true for any choice of G. What would be a good choice of G for the first relation? E2. Excellent. So let's take G equals E2 in the first and G equals E1 in the second. And now we would get E1, E2 is E2, E1 is G, which is just E2. And we would get, in the second one, we would get E2, E1 is E1, E2 is just E1. Thus, E1 equals E2. And so this is a proof that the identity element is unique. And so how did I prove this? I wrote down, what am I given? Here, I'm assuming that I have two identity elements. And so what does it mean to be an identity element? It means no matter what element G you take, EG equals GE equals G. So let me write that down for each one of them. And this is true for all choices of G. Is there a choice of G that's better than others? And for the first one, it's like, well, if I take G to be E2, that's going to give me a relationship involving E1 and E2. And then the other one, if I take G equals E1, that again gives me a relationship involving E1 and E2. All right, and so now I'll leave for you, now prove that each element of G has exactly one inverse. We know it has at least one because to be a group, every element has to have an inverse. So you now have to prove that you can't have two inverses. Okay, so the next thing is some notation. So we'll say the order of a group G, and this is not a social media post, is we write it as $G. It's the number of elements, it's the cardinality. And so if you have a finite set, this is just going to be the number of elements in your set. Other notations are O of G for the order, or the absolute value of G. If you think about it, you've already seen this either abuse or generalization of notation, depending on your point of view. When you first saw absolute values, you probably just did it for integers. The absolute value of 5 is 5, the absolute value of -5 is 5. Then you might have seen the absolute value extended to complex numbers. The absolute value of x plus iy is the square root of x squared plus y squared. Then you might have seen the absolute value generalized to vectors. The absolute value of v is the square root of the sum of the squares of the entries. Sometimes they do double absolute value sign. They do double vertical lines. When you did linear algebra, did they do the double vertical lines or the single vertical lines? Double? Single? Yeah, different people use different things. It's not bad to override the notation and essentially say, what does the absolute value mean? It means the length. You're measuring how much do you have. And if you view it like that, it's not unreasonable to use that for how many elements do we have. And so the proposition we now have is, imagine you have a group G, you choose some element, and let's let n be an integer such that when you raise G to the nth power, you get the identity element E. Then the claim is the order of G divides n. So the order of G is the smallest positive integer, k, such that G to the k equals E. K can depend on G. So I'm not saying every element has the same order. I could write K sub G to remind myself that this K depends on G. If I were to do stuff like this, the notation would quickly become overwhelming. And so we'll just keep it simple and we'll say, look, for this problem, K is going to be the order of G. And it's going to be the smallest positive integer. If I give you the element E, the identity element, what should the order of the identity element be? What would you guess for the order of the identity element? Yeah, 1. It's already the identity. So if you just take it to itself, you get back the identity. So we want to show that no matter what n you take, if G to the n equals E, K divides n. Must show K divides n. Claim that n must be greater than or equal to K is the smallest positive integer. If it's smaller than K, then that would contradict that K is the smallest power of G that gets us to E. So I can assume that n is at least K. Write n as some multiple of K plus a remainder, where the remainder goes from 0 all the way up to K minus 1. So this is just division with remainder. You give me a number, I divide by K, and then the remainder has to be strictly less than K. If the remainder was greater than K, I could have removed an additional. So I keep subtracting K from n until I've subtracted so many multiples that what's left over is between 0 and K minus 1. Is everybody comfortable with this? If not, we can start proving stuff like this and then we'll never get anywhere. At some point, you have to say, I'm willing to accept results. Thus, if I look at G to the n, that's G to the qk plus r. That's G to the qk, G to the r, just hard multiplying all my powers. That's the same as G to k to q, G to the r. What does G to the k equal? E. So again, being extremely pedantic, that's E to the Q, G to the R. What does E to the Q equal? E. So this is E times G to the R, which is just G to the R. This was a lot of steps to just get to G to the R. If you want to say, look, once I have it like this, I know G to the K is E. Let me just go from this to clearly E to the Q is E. E times anything is whatever that is. Let me just jump to G to the R. Okay, fine. Very beginning of the semester, I am showing all the details. I don't know how much longer I'll be able to do this without going crazy and driving people out of mathematics, but it's good to just see all the steps that you have to do at least once or twice. So now we know K is the smallest positive integer that works. R is less than K. So what does R have to be? has to be 0. Thus, n equals q times k, so k divides n. And we're done. And so there's the proof. So we just showed that if I give you some element g, then the only powers that work are all going to be multiples of a fixed power. Then the question becomes, well, what is that k? How does that k depend on the element? If I give you different groups g and different elements in the g, how do you find the k that works? And that's something that we're going to have to spend a lot of time, and it's going to depend greatly on the group. We just know something like this exists. Okay. So now we have lots of different examples of groups in section 3. So we have the group of integers, and then the group of integers modulo m. This is the clock arithmetic. We have the additive groups of real, rational, and complex numbers. We have some multiplicative groups involving real, rational, and complex numbers. We have cyclic groups. We have permutation groups. We have matrix groups, dihedral groups, quaternion groups. There's lots of examples of groups. And depending on what you're studying, different examples come up as being important. Let's look at example 2.19, permutation groups. We basically almost proved that the permutation matrices form a group. What was the identity element? Do nothing. So what matrix is the identity element? The identity. And then the permutation followed by permutation is still a permutation, so it's closed. Does it have an inverse? Yes. Just reverse all the arrows. Instead of sending I to j, send j to I. And then associativity. And this is where arguments are going to be really nice. Because matrix multiplication is associative and permutation matrices are matrices, they inherit associativity. So because matrix multiplication is associative, I don't have to prove it's special just for permutation matrices. I know it's true for all matrices. So I'm going to just forget for a moment that permutation matrices are special matrices. They're just matrices, so it's associative. So permutation matrices work. So let's consider rational numbers under multiplication. Is this a group? Is it closed? Is a rational times a rational rational? Yeah. Is it associative? Yes. Why? Because it inherits it because they're real numbers. Do we have an identity element? Yeah. The identity element is 1. And so if I give you a rational like 3/5, does it have an inverse? And the inverse would be 5/3. So are the rational numbers under multiplication a group? Ah, yes. So there's the issue with 0. Does not exist. So unfortunately, the rational numbers are not a group under multiplication. They just barely fail. So what we can do is study either Q plus, which is the positive rationals, or Q minus 0, which is often written as Q times, which is the non-zero rationals. Those would be groups. And so they will still be closed, and you have to just make sure, because now we're restricting something. Okay, well, nothing was going to be multiplying, so we're okay. All right, so now let's try to think of other possible examples. If I give you matrix addition, that's not going to be a problem to show that it satisfies all of these conditions. Let's look at maybe a clock group. At a clock group, we would say n equals 12 under clock multiplication. The question is, if I look at a clock group, will every element have an inverse? So my set So is there any element that might not have an inverse on a clock? 2. What else? There's a more natural one. So 2 is bad, and we'll come back to 2. It's similar to the problem with the rational numbers. 0. So clock group with an equal underclock multiplication, and we'll remove 0. Because we know 0 is not going to have an inverse. So let's remove 0. The problem is still trouble. If we wanted to solve for the inverse of 2, we want that to equal 1 mod 12. That means, 2x equals some multiple of 12 plus 1. What can you tell me about the two different sides? Yep. So one of them is odd, one of them is even, so it's impossible. So unfortunately, if I look at the clock groups, I know there's going to be trouble with 0. So let's throw away 0. Okay, so we've thrown away 0. That's not enough. We can still have trouble with elements such as 2. So at this point, we should do a lot of investigations and try to figure out which clocks form groups. So can anybody give me a good clock to try? You're really going to get to 13. Let's give a smaller one. Let's be nice. Let's play nice. Today's be nice to your professor day. 5. All right. I have two numbers that don't share a factor with 5. When I multiply, they're not going to share a factor with 5. Is there an identity element? Yeah, identity is 1. It's still associative. And now we need the inverses. So can anybody give me an inverse to 1? 1. So what times 2 equals 1 on a clock with 5 hours? 3. 2 times 3 is 6. So 2 inverse is 3. So if 2 times 3 is 6, 3 is the inverse of 2. It should now be very easy to calculate the inverse of 3. Right? If 2 times 3 is 1, and 3 is functioning as the inverse of 2, what's functioning as the inverse of 3? 2. Or just take the inverse of both sides, and 2 inverse is 2. Now, here's the fun one. What is 4 inverse? How did you get that? So you could view 4 as it's -1 on the clock, and then -1 times -1 is 1. So squaring 4 should work. That is one way to do it. And so I hope section 1 doesn't listen to this part. This is the advantage of being in section 2. We know inverses are unique, right? Can we say that the inverse of 4 has to be 4 because nothing is left? If we knew it was a group, yes, but we don't know it's a group. If we knew it was a group, then the only thing that's left is 4 because 1, 2, and 3 are taken. Okay, we don't know it's a group, but if it's going to be a group, the only possibility for 4 inverse is 4, so I might as well just try that. And it works. So we now have 2 data points. When n equals 5, it's a group. When n equals 12, it's not. What I'm going to do is I'm going to make a little table. Here is n. Is it a group? The answer is yes. 3, yes. 4, no. 5, yes. 6, no. 7, yes. 8, no. So we've just fast forwarded an hour in time. We've gone through, and for each one of these, we investigated and we tried to find inverses, and we found that it worked for the following. It worked for 2, for 3, for 5, for 7, for 11, for 13. And it failed for the rest. Does anybody want to conjecture which ones it works on? Prime numbers. So looking at this data, we might conjecture that if you look at the clock with the prime number of hours, the non-zero elements are invertible. And so let's keep that. So clock in the multiplication. Okay, so now we want to prove that if you look at the non-zero elements, it can't be a group. So you have to show one of the 4 properties is violated. Either it doesn't have an identity, it's not closed, it doesn't have an inverse, it's not associative. Any properties you think are going to hold? Yeah, hold, be true. Closed. Why closed? But okay, so if they're not zero, then
not zero.
so closed could be a little bit harder. There's one that should be really obvious that this should still hold. Identity. It inherits the identity. Associativity, it inherits that. Closure and inverses are more interesting. So now, claim A inverse does not exist. In fact, if it did, then x times A equals A times x equals 1 on a clock with AB hours. So that means AX is some multiple of AB plus 1. So if I subtract AX minus NAB equals 1, and so I get A times X minus B equals 1, therefore A divided. So here's one way to show that it's not a group. A inverse doesn't exist. Why was A inverse a natural thing to look at? So I know that n equals A times B, n is composite, so I'm trying to use the information from the problem. So as soon as I write n equals AB, A and B are special numbers. They have some play with n. And so when I look at it, let me try to find the inverse of A. What else could I have tried to find the inverse of? B. But of course, A and B are essentially the same. As a bonus, it's not closed. A and B are non-zero, but AB equals 0 on my clock. So it feels closure, it feels inverses. This is not a group. So one of the really good phrases in mathematics is prove, disprove, and then salvage if possible. So when we look at this, we see that if we look at the non-zero elements on a clock, it's not a group under multiplication. And we thought we were doing a good job. We got rid of 0. We know 0 can be problematic, so let's look at the non-zero elements. Getting rid of 0 was not enough. Can you think of other elements we might need to get rid of? Okay, good. So let's try that. So look at all numbers relatively prime to n on our clock. For example, n equals 12. What's the first number that's relatively prime to 12? 1. 2 shares a factor. 3 shares a factor. 4 shares a factor. 5 does not share a factor. 7 does not share a factor. And 11 does not share a factor. So you can see that 8, 9, 10 will all share factors. So I now have 4 elements. Is there an identity element? Yeah, it's 1. What about associative? Will it still be associative? Yeah, it inherits it. So inheritance is good, right? So as long as we know that the full clock group is associative, if I just restrict myself to a subset of elements, it's still going to be associative, right? So identity is easy, and associative is easy. So this is a general rule. Typically, identity and associative are the easy ones to check. The harder ones are the closure and the inverses. What was nice about the last problem is they both failed. So it didn't really matter which one we checked, we would quickly come up with a problem. So for closure now, we just have to look at all the multiplications. So there's 4 elements. Each one can be multiplied, so that's 16. Is it really as bad as 16? Why not? But I'm saying there's 16 possible multiplications I have to do. Choose one of the numbers, and then choose another number, and then multiply them. Why is it not as bad as 16? Yeah, 5 times 7 is the same as 7 times 5. So I only have to choose 2 numbers from this set. How many ways are there to choose 2 distinct numbers? 4 choose 2. How many ways are there to choose the same number twice? 4 choose 1. 4 choose 2 is 6. And 4 choose 1 is 4. So there's really only 10 multiplications to do. It's closed. Okay. We just did the 10 multiplications, okay? 1 times everything is easy. So we just have to do really 5 times 5, 5 times 7, 5 times 11, 7 times 7, 7 times 11, 11 times 11. What's nice is I've chosen the numbers that are relatively prime to 12. So if I take 2 numbers that are relatively prime to 12 and I multiply them, they're still going to be relatively prime to 12. And so when I reduce by subtracting multiples of 12, it's still going to be relatively prime to 12. You should write this up rigorously. You should not be doing the hand waving that I'm doing. I get to do this as a professor. It's good exercise for you to just try to write this up, or just be convinced that you could do it, that you could put in the details if you had to. So the only thing that's left is finding inverses. One of my favorite proofs is the method of divine inspiration. The way the method of divine inspiration works is you write down the answer and you see it works. Anybody want to guess what the inverse of 1 is? 1. So I need something times 5 has to be one more than a multiple of 12. It can't be one, right? Because we know every element has a unique inverse if it's going to be a group. Any thoughts about what the inverse of 5 might equal? 5. 5 times 5 is 25. What about 7? What times 7 is one more than a multiple of 12? 7. 7 times 7 is 49, which is one more than 48. And 11, what's the only thing that's left if it's going to be a group? 11. And if you try it, it turns out 11 times 11 is 121, which is one more than a multiple of 12. What's interesting is x squared equals 1 mod 12 has 4 solutions. Okay. So this is going to show you that things are a little bit different when we look at a clock. If I give you x squared equals 1 with just standard regular functions, with real numbers, complex numbers, x squared equals 1 is going to have exactly 2 solutions. They don't have to be distinct, but a polynomial of degree 2 has 2 roots. A polynomial of degree 3 has 3 roots. Here is a polynomial of degree 2, but it has 4 solutions when we look at it in this space. This is interesting, right? And so here we now have a interesting example of a group. And this is during the special case when n equals 12, and we're looking at the non-zero elements. So then the question becomes, what if I look at other ones? Do I think the non-zero elements will always work? What are your thoughts? So we could do some experiments, right? I gave you a table. It's really good to learn how to do some coding. We could investigate a large number of choices of n that are composite. We could take an n that has 3 factors. Let's gather some data. What's the next simplest n that you might want to do after 12? Will be another good n to take. So you could do 14, and that's going to again be 2 distinct primes. 12 was 2 squared times 3. What else could you do? What might be another interesting one to choose? So I think 14 is a great one to check, but 14 maybe is similar to 12 in that it has 2 30. Maybe try n equals 30. Look at relatively now this is more interesting. Look at that one. Don't have 2, don't have 3, don't have 4, don't have 5, don't have 6. We have 7. Don't have 8, don't have 9, don't have 10. We have 11. Don't have 12. We have 13. Don't have 14. Don't have 15. Don't have 16. Have 17. 18? Nope. Any even number we don't have. 19, we have 19. Oh, this is just the primes. What do you think? So here, it's got to be. So I can't do 7 times 7 is 49. It's too small. So it's actually going to just be the prime. So it's 19, 23, 29. In general, however, it's not going to be that. This is the danger of looking at small things. If I had done 2 times 3 times 53, which is a prime, then I could have had 49. And so again, this is the 16/64 problem. If you look at a small data set, things can be misleading. Identity, yay or nay? Yeah, it's 1. Associative. Yeah, it inherits that. Closure. Yeah, if you're relatively prime, so the only thing that's difficult is the inverses. Now, as was remarked, the halfway point is 15, right? So I can write this as, 1, 7, 11, 13. And then on this side, this is 30 minus 1, 30 minus 7, 30 minus 11, 30 minus 13. And so if I can find the inverse of 7, I should be able to find the inverse of 30 minus 7 without too much trouble. So again, part of this is just to try to make my life easier, or your life easier if I'm passing the work on to you. Let's try to find inverses. Well, what we saw before is it seems like every number's inverse is itself. Do you think that still is true? It's a shame. It would be really nice, wouldn't it? What is the inverse of 1? Maybe it's still true. All right, so 7 times 7 is 49, which is not 1 mod 13. 1 mod 30. Okay, so the inverse of 7 is not 7. It's not 1. All right, we've got to keep trying various things. So we need to be 1 more. So the first thing it could be is something times 7 31? No. No, no.
Oh,
Right. Yeah. So nothing times 7 is 31. The next candidate would be 61. Is there anything times 7 that will give me 61? 61 is prime, so it's not going to happen. So now 91. Is anything times 7 91? 13. Okay, and so we've now found the inverse to 7. And that's enough to show that, unfortunately, the inverse is not always just the inverse of the number. Oh, well. What about 11? This is kind of nice. 11 times 11 is 121. 121 is a multiple of 30. I'm sorry, 120 is a multiple of 30, so this is 1 more than a multiple of 30. So again, you could do this all by brute force. Now we need the inverse of 13. You should be able to get that immediately. What's the inverse of 13? 7. If the inverse of 7 is 13, the inverse of 13 is 7. So now I need to do the next ones. So now, what would be the inverse of -1? Would just be -1. So 29 inverse is just going to be itself. And you should really view this as -1 inverse is -1. Now I need 23 inverse. This is the same as 30 minus 7 inverse, or it's really the same as -7 inverse, or -1 inverse 7 inverse. What's the inverse of 7? 13. The inverse of -1 is -1. So it should just be -13. So I would guess that this should be 17. Sadly, we still have some time left today. 23, 17, 7 times 3 is 21, 14, 15, 16, 23. So 1, 9, 3. We want to see, is this a multiple? Is this one more than a multiple 30? Yes. This is 30 times 130 plus 1. Did I make a mistake? 13, not 130. Thank you. So We could have just, gone through and tried things to find that 17 was the inverse of 23. We also know there's not that many candidates left at this point. But the faster way is to say, well, 23 is really the same as 30 minus 7. That's really the same as -7. The inverse of a product is the product of the inverses in reverse order. I know what the inverse of 7 is, that's 13. I know the inverse of -1 is just -1. So this is just going to be -13, and -13 is the same as that. All right, so now I just have to continue. Now I would have the next one would be 19 inverse. And so 19 is the same as 30 minus 11 inverse, which is the same as -11 inverse, which is the same as -1 inverse, 11 inverse. The inverse of 11 is 11. The inverse of -1 is -1, so it's -11. So that's just 19. And then we're left with 17 inverse, which of course has to be 19 because, sorry, it has to be 23. So this is a more interesting example. This is still far from a proof, but we're gaining some confidence now that it looks like we are able to find inverses. We're also seeing that there's not a nice formula. The fact that the inverses, when we had a clock with 12 hours, were just the elements, that doesn't continue, unfortunately. But maybe there is a structure to the multiplicative elements. And this is actually going to be one of the key items when we do cryptography later in the semester, is we're going to need to look at clocks with a prime number of hours or the product of two distinct primes. And so we actually don't need to really look at clocks that are, the product of 3 primes, but the general theory isn't that much worse, so we'll do the general theory. Okay, so this is a good place to stop. So we did a lot today. We saw the definition of groups. We saw how to use some of the proof techniques we talked about before, such as induction. We saw that when you're trying to prove something is true, that frequently there are clues from the statement. At this level in your career, if there is a condition in the theorem, almost surely that's necessary. You can play games such as, do I need both the left identity and a right identity? If something is a left identity, does that mean it's also a right identity? And you can try to figure out what is the weakest set you need. When I prove the fundamental theorem of calculus, I assume my function is not just continuous, but it's continuously differentiable. I don't need to do that, but it allows me to bypass some results from real analysis and make the proof simpler. So sometimes if you remove conditions, the proof becomes harder, but the result is still true. So when you're trying to understand things in the book, it's always, why are we assuming these conditions? Is it true in more generality? Well, the examples we're looking at, it's really not that big of a deal to be assuming we have a left and a right identity. We're always going to have that, so we're not going to really worry about it, but it's something to consider. When you're trying to show something is not true, you just have to find one place that fails. And so if we have 4 properties, which property should we zero in on? Frequently, some properties are always going to hold, so it's not going to be that much work. Identity is usually pretty clear. Associativity is usually inherited. It's the inverses and the closure that's more likely to have problems. If I give you the integers, is there an integer? So I give you, say, the non-zero integers. Does 2 have an inverse? Multiplication. Is there a multiplicative inverse for 2? Does something times 2 equal 1? 1/2. So 2 has an inverse, and it has such a famous inverse, we've even given it a name, 1/2. But it's not an integer, so it's not closed. So even though the inverse exists, the inverse is not in the set. So the set of integers that are not 0 under multiplication is not a group. That's why you have to extend up to the rational numbers. All right, so I am traveling today, so it'll be a while before I post. I may not post till late tonight or early tomorrow morning. I'm going to stop here.